Now we're going to talk about a function which is really important for talking about discrete time signals, and that's called the delta function, or the unit impulse function in discrete time, sometimes also called the Kronecker delta function, named after a mathematician named Kronecker. So our objectives for this video are to explain the impulse function and to be able to write discrete time signals as sums of impulse functions. So it turns out you can write any discrete time signal as a linear combination of impulse functions, and we'll see why that is. It's fairly straightforward. And then we're going to use this Kronecker property to simplify multiple summations involving impulse functions. So that will appear a bit later, when you have to do some calculations to solve some problems. So the unit impulse function is very simple. It's 1 at time 0 and 0 everywhere else. So it's just a unit impulse. That is, it takes some value 1 at one point, namely at n equals 0, and then it's otherwise silent. It doesn't have any values anywhere else. So more generally, if you have delta of n, or delta of something, the delta function says, check when the something inside the brackets is equal to 0. And when it's equal to 0, then the answer is 1, and otherwise it's 0. So that's why it's called an indicator function. It indicates whether the inside is equal to 0. So let's see a quick example of that to make it a little bit more clear and less abstract. So if we look at delta of n minus k, here we're looking at delta of n minus 2. Then we're looking at when is n minus 2 equal to 0, and that's when n equals 2. So therefore we have just this unit impulse function at time 2. Now sometimes you see it drawn with a like this. We call it like kind of lollipop, or the open circle. MATLAB draws it with open circles. So this is what's just representing a discrete time signal. So it turns out that all discrete time signals are just sums of shifted and scaled discrete time functions. So if we look at this signal here, for example, this is delta of n plus 1, that covers this guy, and then plus, say, I think it looks like 3 halves delta of n, that's this one, and then maybe plus 5 halves delta of n minus 1, that's n minus 1 is at time 1, plus, minus 2 delta of n minus 2. Right, and that's this one here. So this is what's called we can think of this as the sampling property of the delta function. So if I look at the summation of x of k from k equals minus infinity to infinity and I multiplied x of k by delta of n minus k, this thing here is just checking when it checks when k is equal to n. When k is equal to n, then we get that this thing here is equal to 0, and we're only going to pull out x of n. And here we go, we have x of n on this side. So this is what's called the sampling property of the discrete time impulse function. It can pick out one element of the sequence xk. So for finite discrete time signals, we sometimes just write them out in terms of delta functions. So here's another example like the one that we saw on the previous slide. So here, this thing would be 2 at time equals 0, then it's minus 3 at time equals 1, and then it's 4 at some time k, here's k, and it's equal to 4, so 4 is probably up here, something like that. So we can also write the unit step function. The unit step function is just the sum of shifted delta functions starting from 0 to infinity. So that's just 1 when n is bigger than 0 or equal to 0, and 0 everywhere else. And that's what we saw as the definition of the discrete time unit step function. So a situation you might find yourself in doing calculations is you get these kind of double or triple sums involving lots of delta functions because they involve several discrete time signals, and then you're trying to put these discrete time signals together in some way, and then you end up with, and one of them is a sum of delta functions, the other one's a sum of delta functions, so now you have two sums of delta functions, like in this example here, where I can use this sampling property to represent h of n, the signal h at time n, using this this sampling representation of the delta function, and similarly I can represent x of n the same way. And then if I want to compute something which we call the discrete convolution of h and x, that's given by this. So this is the dt convolution. We're going to see this later in much more detail. But just take this as a definition. Then we would like to be able to, calculate this, but this is going to be a sum. So this thing is a sum, this thing is a sum, so that's 3 summations. So let's take a look at what that might look like. So for example, in the example given at the bottom of the previous slide, we plug in h and x into the formula. So here's h and here's x. We had and so now we gather all the summations together and we get 3 summation terms, which is a lot. And then we have this 1/2 times k, and then we get the product of these 2 delta functions. So now it's like this does not seem to have made our life any easier in terms of solving the problem. But first you want to use the property that delta of stuff is only equal to 1 when stuff is equal to 0. So in particular, this delta of m minus k here, this delta of m minus k is equal to 0 unless m equals k. So when does m equal, so the question is, when does m minus k equal 0? Well, when m equals k. And so at that point, this delta function is 1, otherwise it's 0, which means that we can reduce these 2 summations over m and k into just a summation over k, because m is equal to k. So that gives us our representation of yn in terms of a double sum. Now the question is, can we do any better than that? And the answer is, of course, yes. Why would I bother making these slides if you couldn't get a little bit farther than that? So let's look at y of n. We have to look at this other delta function, this other Kronecker delta function. Now that's equal to 0 when n minus k minus l is not equal to 0. So, or put the other way, this thing is equal to 1 when n minus k minus l is equal to 0. So we can wiggle that around into a condition on L. L has to be equal to n minus k. And we have n here, and we have k here, so I can get rid of one more summation, and the summation basically can only go from k equals 0 to n. So when k used to go from 0 to infinity, but can really go only from 0 to n, because we need to have this condition that L is equal to n minus k. Okay, so we end up with this solution, and now we can do even more. We can remember our geometric series and take the summation of 1/2 to the k from k equals 0 to n. We can use our partial geometric series, so I guess it's a partial geometric series, to get an even simplified solution. And we can do some more algebra if you want. Algebra to get an even simpler solution. So this preceding discussion shows you that you can use these delta functions to simplify like triple summations into something more tractable, and then you just get a number as an answer, which is pretty cool. I recommend going through just writing it out, this previous example, maybe change it to 1/3 to the k or something like that for instead of 1/2, just to get a sense and make the arguments for yourself so you can see how it works, because that'll make it a lot clearer. So the last thing you can do with delta functions in discrete time is you can make what's called an impulse train. So for example, if I take this summation of delta of n minus k times capital N, then this thing is equal to 0, this internal part is equal to 0 when n is equal to k times n. So when n is an integer multiple of capital N. And so, for example, if capital N was equal to 5, we would get this picture here. This corresponds to n equals 5. And basically getting 1s every 5 samples. And so you can see this is sort of related to downsampling and upsampling even when you think about working with discrete time signals. So these impulse trains are going to be pretty important when we talk about doing signal processing. So just as a wrap up here, you should try sort of working with delta functions to get comfortable with them, so that because we're going to be working with them extensively in the rest of the class. So try to write down these three signals, try to use the sampling property to generate waves, the square wave and the triangle wave, and just try to use the direct representation where you write out a signal in terms of delta functions for this first one. So this is the discrete time delta function, and in continuous time we also have a delta function that's called the Dirac delta function, and we're going to look at that one next.